Now that we understand something about valence electrons, we can look into what we call our bonding theories. In chemistry, bonding is the way that we describe how atoms attach to one another to make molecules, or how cations and anions interact to form ionic compounds. An understanding of how and why atoms attach together in the manner that they do, or ions attach to one another, is central to chemistry, because the breaking of bonds and the forming of new bonds is how chemical reactions occur. Some of the powerful tools we've gotten from our bonding theories is it allows chemists to predict the shapes and properties of molecules based on the type of bonding there is within the molecules. This has allowed us to design and build molecules with a particular set of chemical and physical properties. So an example would be the designing of medicines or drugs to fulfill a certain purpose. These kind of tools and knowledge are critical in chemistry. A relatively simple theory that is very powerful to help describe molecular and ionic bonding is what's known as the Lewis theory. The Lewis bonding theory emphasizes the importance of valence electrons, and what we do is we use dots to represent valence electrons that are either on an atom or shared by atoms in a molecule. And we arrange our bonding electrons between atoms to attain a certain set of stable valence electron arrangements. And as you might have guessed, this stable valence electron arrangement is going to be the same valence electron arrangement that noble gases have. 2 for helium and 8 for all the other noble gases. Let's take a look first at the Lewis symbols of atoms. This is also known as electron dot symbols or Lewis electron dot symbols. The way that we write them is we use each elemental symbol to represent the nucleus of the atom as well as the core electrons. And then we place the valence electrons around it. And we do it in a very specific way. Each valence electron is represented by a dot, and we place our first 4 valence electrons around the symbol 90 degrees apart from one another, and then we start pairing. So here we are with lithium, beryllium, boron. It doesn't matter whether you start on the right or on the bottom, on the left or on the top, but what does matter is that wherever you start, your next one is 90 degrees apart. And then once we get 5, 6, 7, 8, we start pairing. Now elements in the same group or column are going to have the same number of valence electrons, and therefore their Lewis dot symbols will look alike. So remember, we can count our number of valence electrons for our main, sorry about that, I'm not sure where I was, but valence electrons for main group based on their column. So 1 valence electron, 2 valence electron, 3, 4, 5, 6, 7, 8, except for helium, which has 2. So lithium has 1 valence electron, so does sodium, potassium, rubidium. So if I was drawing the Lewis dot symbol for sodium, I would just have an Na here with the dot. Or if I was drawing it for calcium, which is in the same family as beryllium, I'd have a Ca and then 2 dots, etc. So pause the slide and see if you can write the correct Lewis symbol for arsenic. The first thing we need to do is find arsenic on the periodic table, and here it is in family 5A, the nitrogen family. That is 1, 2, 3, 4, 5 columns over, so there are 5 valence electrons. So your Lewis dot symbol should look something like this. Now it doesn't matter if your paired electrons are on the top or on the right, bottom, or left, but they should all be 90 degrees apart, and you should only have 1 set of electrons that are paired to represent the 5 valence electrons of arsenic. Now let's look at the basis for that Lewis bonding theory. Atoms bond because it results in a more stable electron configuration. Remember, atoms want to be like the noble gases. So atoms will bond either by transferring electrons, which will occur in the case of ionic bonding, or sharing electrons, which will happen in the case of molecular or covalent bonding. Usually, this is going to result in all atoms obtaining an outer shell with 8 electrons. What's so special about 8 electrons? It's the number of valence electrons that noble gases have. We call it the octet rule. Now, there are going to be some exceptions to the rule. And the first exception we're going to look at is lithium, beryllium. Let's put hydrogen in here too. And hydrogen, are going to achieve the helium electron arrangement. Lithium has 3, beryllium has 2, and hydrogen have 1 electrons. So this is closest to helium, which as a noble gas has 2 electrons, a filled s subshell. Now let's take a look at the Lewis symbol of ions. And what we care about is the number of electrons. Now, for the cations that we're going to be looking at, we're going to be looking at metals that are near the noble gases. These cations are going to form because they're going to lose all their valence electrons to become like a noble gas electron configuration. They lose their valence electrons in the chemical reaction, and they now have a full outer shell that is similar to the nearest noble gas. And then anions are going to gain electrons so that they have 8 valence electrons. So let's look at lithium. Here is lithium as an atom. Lithium is in the first column, so it has 1 valence electron. But as a cation, it loses that 1 valence electron to get a positive charge and therefore has no valence electrons. Fluorine, as an atom, has 7 valence electrons. All halogens have 7 valence electrons. Being 1 electron away from a noble gas configuration, halogens like to gain an electron. And we put this symbol in brackets to give it some extra emphasis to show that it has an extra electron and it has 8 electrons around it, and we also put its negative charge, as always, in the upper right-hand corner.